Testing, can you hear me? Okay, so this video is public now. So I'm going to be learning about computer architecture again. It's been quite a while, so I may need to review some things. Hold on. So this is the book I was reading. The website lost its expiry, so now it says not secure. Anyways, so I read up till this assembly language. Uh, I read up till SimpleRisc. I haven't read this chapter yet. Last stream I was reading about assembly language, but I'm going to do some review about certain things. So, firstly is the ISA. Yeah, the semantics of all instructions supported by a processor is known as the instruction set architecture. This includes the semantic of the instructions themselves, along with their operands and interfaces with peripheral devices. First, I'm going to add this to my notes, make this small, make this small. And I will put this bold. I mean, I don't see the difference clearly. Anyways, so this part I wanted to review. Another thing is that the ISA has to be complete, concise, generic, and simple. Okay. So the ISA should be able to implement all user programs. So it needs to be complete. It needs to be concise. We should ideally not have a lot of instructions. Needs to be concise. It needs to be generic. Instructions should capture the common case. It is not a good idea to have instructions that implement a very rarely used computation. Makes sense. Wait. Yes. And lastly, it should be, yeah, it should be simple. And by simple, they mean let us assume we have a lot of programs that add a sequence of numbers. To design a processor specially tailored towards such programs, we have special options with regard to the add instruction. We can implement an instruction that adds two numbers, or we can also implement an instruction that can take a list of operands and produce the list produce the sum of the list. There's a clear difference in complexity here, and we cannot say which implementation is faster. Former approach requires the compiler to generate more instructions. However, each add operation executes quickly. The latter approach generates a fewer number of instructions, but each instruction takes longer to execute. The former type of ISA is called a reduced instruction set. The latter ISA type is called complex instruction set. So a reduced instruction set implements simple instructions that have a simple regular structure. Number of instructions typically small number. So that's an important point. The other important point is a complex instruction set computer, typically 500 plus. Wouldn't this one over here break this simple rule? We need ISA to be simple, right? I guess it's subjective what they mean by simple. The ISA needs to be these things. It is necessary. However, since the designers, programmers, and processors vendors have been tilting towards the RISC design style, the consensus seems to go for a few relatively simple instructions that have a regular structure and format. And another thing I wanted to review is page 28. Yeah, first, this chapter is a prerequisite for the next chapter on assembly language. We read about assembly language. We read about what it is, but we didn't do any assembly language. Assembly language is a textual representation of an ISA. It is specific to the ISA. Since an instruction is a sequence of zeros and ones, it is very difficult to study it in its pure form. Assembly language gives us a good handle to study the semantics of instructions in an ISA. Chapter 3 introduces the general concepts and serves as a common introduction to the next two chapters that delve into the details of two very popular real-world ISAs, ARM and x86. So chapter 4 and chapter 5, they talk about ARM and x86, but this chapter 3, what I'm reading right now, it talks about SimpleRisc, which is a simplified version. We introduced a simple ISA called SimpleRisc in chapter 3. Subsequently, in chapter 4, we introduce ARM, and chapter 5, we briefly cover x86. Note that it is not necessary to read both these chapters. After reading the introductory chapter on assembly language and obtaining an understanding of the SimpleRisc, the interested reader can just read one chapter. But I guess I will just read both of them. I genuinely want to get an understanding on ARM, and I think my laptop uses the x86. So SimpleRisc. This is where I left off last time. This book, which will introduce a simple, generic, complete, and concise RISC ISA called SimpleRisc. The assembly language of SimpleRisc has just 21 instructions and captures most of the features of full-scale assembly languages. We will use SimpleRisc to demonstrate the flavor of different types of assembly programs and also design a processor for the SimpleRisc ISA in Chapter 9. We shall assume that SimpleRisc assembly follows the GNU assembly format. Yeah, I forgot what this is, GNU assembly format. Before proceeding further, let us take a tour on different instruction sets and take a look at their properties. In chapter 1, we looked at properties of different instruction sets, including necessary and desirable properties. In this book, we shall describe two real instruction sets, namely the ARM and x86. ARM stands for Advanced RISC Machines. It is an iconic company based out of Cambridge. As of 2012, around 90% of mobile devices, including the iPhone and iPad, run on ARM-based processors. As of 2012, more than 90% of desktop and laptops run on Intel or AMD-based x86 processors. ARM is a RISC instruction set. x86 is CISC instruction set. There are many instruction sets tailored for a wide variety of processors. Another popular instruction set for mobile computers is the MIPS instruction set. MIPS-based processors also use are also used in a wide variety of processors used in automobiles and industrial electronics. Yeah, I don't know what. So vendor, we have Intel, we have ARM. ARM is advanced risk machine. MIPS is another one. Intel or AAT. For large servers, typically IBM, Sun, or HP processors are used. Each of these processor families has its own instruction set. These instruction sets are typically RISC instruction sets. Most ISAs share simple instructions such as add, subtract, multiply, shifts, and load store instructions. However, beyond this simple set, they use many more specialized instructions. As we shall see in the next few chapters, choosing the right set of instructions in an ISA is dependent on target machine of the processor, the nature of the workload, and many design time constraints. SimpleRisc assumes that we have 16 register numbered R0 to R15. The first 14 registers are general purpose and can be used for any purpose within the program. So we have SimpleRisc. I'll just write SimpleRisc over here. It's SimpleRisc time. This is going to be Excel. So with SimpleRisc, we assume that there are 14, 15 registers. Can I draw a line somewhere? Okay, never mind. So 15 registers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 12, 13, 14, 15. This is R0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So there are 16 registers, right? And then lastly is R15. I think it's better if I write it the other side. R15, R0. First 14 registers are general purpose registers, can be used for any purpose within the program. Okay. Uh, General purpose. And then just write this in blue. Register 14 is known as the stack pointer. We shall also refer to it as SP. So register 14 is the stack pointer. Register 15 is known as the return address register, and it is also referred to as RA. RA. We shall discuss SP and RA when we discuss how to implement functions in SimpleRisc. Each register is 32 bits wide. We assume a special internal register called flags, which is not visible to the programmer. It contains two flags, e flags.e and flags.gt. These two registers are separate, right? So separate, and this is 32 bits. So we have 32 bits. And then we have flags E, flags GT. E, GT. E is set to 1 if the result of a comparison is equality, and GT is set to 1 if a comparison concludes that the first operand is greater than the second operand. The default of both the fields are 0. Is it all? It's 1 bit, right? Is this 1 bit? I should just add a text. Default 0. Each instruction is encoded into a 32-bit value and it requires 4 bytes of storage in memory. SimpleRisc assumes a memory model similar to the von Neumann machine augment. Von Neumann machine augmented with registers as described in section 1.7.3. The memory is a large array of bytes. A part of it saves the program and the rest of the memory is devoted to storing data. We assume that multi-byte data types such as integers are saved in a little endian format. Each instruction is encoded in 32-bit value and it requires 4 bytes of storage and memory. Uh, okay, register transfer instruction move. The move instruction is a two address format instruction that can transfer values from one register to another or can load a register with a constant. Our convention is to always have the destination register at the beginning. So move register, register immediate. Example, move the value of R2 to R1 or move the constant 3 to R1. I want to write this down. Coded 4 bytes of storage in main memory. Memory model, the memory is large byte of array. This goes here. And then we have the main memory. Main memory. Four bytes of storage in memory. No, wait, how big is the 32-bit? It requires 4 bytes of storage in memory. Okay, never mind this. So each instruction is encoded into a 32-bit value and it requires 4-byte storage in memory. Each instruction requires 4 byte of storage in memory. SimpleRisc has 6 arithmetic instructions: add, sub, mul, divide, mod, compare. The connotations of add, sub, multiply are self-explanatory. For arithmetic instructions, we assume that the first operand in the list of operands is the destination register. The second operand is the first source operand. Third is the second source operand. So add what is stored in these two registers. No, wait. This is the destination, and these two is what we are adding. So add what is stored in this register with this immediate value. Subtract what is stored in this register with this value. So R2 minus R3. Multiply. You have divide. This division is an integer division, right? And then we have mod, which gives the remainder, and then compare, set flag. To compute 31 times 29 minus 15, save the result in R4. So I found this RISC-V web simulator. It's not SimpleRisc, but we haven't done RISC-V yet. So let me just try this. So computer architect, write assembly code in SimpleRisc to compute 31 times 29 minus 15, save the result in R4. So we do move register, right? Move 31. Okay, wait. Move destination 31. Let's run. Unknown operand. They don't have move. No, the RISC-V doesn't do the thing. Settings. How do I find all the thing? Okay, so without looking at the answer, try to write the answer here. Can I draw a box? I can draw text. You can make it a code. Okay, so they said 31 times 29 minus 15. Save the result in R4. So I will do move register. This. Do I need to add a comma? Is that it? No, I think RISC-V is different. When I do RISC-V, maybe I will try that. Move register immediate. So move to R1. The value 39, right? And then move to R2. What did they say? 29 and 31. 31, 29. Move to R3, 29, 31, 29, and 50. Do I need a comma? Is a comma necessary? We did the move. Now we need to multiply. So we multiply this to destination register and then the two operands. So mul destination register and then the two operands. So 31 times 29, store it in R1. And then subtract, we store it in R4, R1 minus R3. We can subtract immediate values, right? So we can just do 50. We can just do 50 here and we don't need this. Actually, we don't need this as well. We just need R1. R1 stores 31. Now destination registers R1, R1 times 29. Yeah, and then what we store in R4 is R1 minus 50. I don't think we even need R1. We can just do everything in R4. R1 stores 31 multiplied by 29 and multiply what is stored in it with subtract what is stored in it with 50. But they did do move. The division algorithm divides the first source operand by the second, computes the quotient, saves it in the destination register. Compute 31 divided by 29 minus 50, but we only get the integer division. We don't get the mod instruction, computes the remainder of the division. Compare instruction is a two address instruction that takes two source operands. First source operand needs to be a register. The second one can be an immediate or a register. If the operands are equal, or in other words, the result of the subtraction is 0, then it sets E to 1. Otherwise, E is 0. If the first operand is greater than the second operand, then the result of the subtraction will be positive. In this case, the compare instruction sets greater than the compare instruction sets greater than to 1. Otherwise, it sets it to 0. So when we do compare, if the two are equal, it sets E to 1. If one of them is greater, if the first operand is greater, then it sets greater than to 1, right? The first operand is greater than is set to 1. SimpleRisc has 3 logical instructions and wait, for the previous one, if the two values are equal, would it set greater than to 0? It would reset greater than, right? And you cannot have 1, 1. SimpleRisc has 3 logical instructions and, or, and not. And or are 3 address instructions. They compute the bitwise and or of 2 values respectively. The not instruction is 2 address instruction that computes the bitwise complement of a value. Note that the source operand of the not instruction can be an immediate or a register. So R1, R2, and R3. So we and or not, okay, they do the bitwise operation. Compute A or B, assume A is stored in R0 and B is stored in R1 and store the result in R2. Or So we do R2. So for this exercise, compute A or B. So, so or instruction destination is R2 and then R0. A or B, store it in R2. A or B, store it in R2. And then we not it. So not R2, store it in R2. SimpleRisc has three types of shift instructions: left shift, logical right shift, arithmetic shift right. Okay, I don't know what this is. I know these two shift the bytes left or right, shift the bits left or right, but I don't know what this is. Each of these instructions are in three address format. The first source operand points to the source. The second source operand contains the shift amount, which can be a register or immediate. The logical shift left instruction shifts the value in the first source register to the left. Uh, and if there's an overflow, we just forget about it, right? Uh, Logical right shift. This means that it fills all the most significant bit position with zeros. Logical right shift. Okay, yeah. So if there is a bunch of bits, 0, 1, 1, 1, 0, 1, 1, 2, 3, 4, 5, 6, 7, 8. If I do a right shift, 1, 0, 1, 1, 0, 1, 0, I get this, and the most significant bit is set to 0. Left shift, logical shift left, logical shift right. Yeah, I don't know what ARS is, arithmetic right shift. Did they explain it? In comparison, ARS performs an arithmetic right shift. It fills all the most significant bits position with values of the previous sign bit. Semantics of shift instructions are shown in table 3.5. What do they mean by previous sign bit? Do they mean something like this? Do they mean this 0, the bit over here goes at the end? Like modulo? Logical shift right. Logical shift right. And then what is ARS? Arithmetic right shift. Because I'm going to guess it does the modulo thing, because I don't know what they mean by previous sign bit. SimpleRisc has two data transfer instructions: load LD and store ST. The load instruction loads values from memory into registers, and the store instruction saves values in register to memory locations. Examples and semantics are shown in table 3.6. Wait, hold on. Yeah, I don't think it's modulo. I think it's something else. 10 shifted to the right. The most significant bit is sometimes used as a sign bit, right? To check whether it's negative or positive. Previous sign bit. So if I shift it to the right twice, the sign bit was 1, and that's what it will fill the most significant bit with. This is my current understanding. I might be wrong. Load and store. So the load instruction loads a value from the main memory into here. Uh, Saves value from memory into registers. Store register saves values in register to memory location. It is considered the load instruction. Load R1, 12 R2. Here we are computing the memory address as the sum of the contents of R2 and the number 12. The load instructions accesses this memory address, fetches the stored integer and stores it in R1. We're assuming R2 stores. R2 is a pointer variable, right? It stores a memory address. We assume that the computed memory address points to the first stored byte of the integer. Since we assume a little alien representation, the memory address contains the least significant bit. The details are shown in figure 3.7a. Store operation does the reverse. It stores the value of R1 into memory address R2 plus 12. SimpleRisc has one unconditional branch instruction B, which makes the program counter jump to the address corresponding to a label in the code. It takes a single operand, which is the label in the program. Its semantics are shown in table 3.7. So branch 2.foo. Let's explain with an example. Load, store. What is stored? The memory address in R2, but plus 12. So what is, so the value here gets stored to R1. Value here gets stored to main memory. And R1, R2, R3, be branch to foo, and then foo contains this. Like, how does this branching work in the assembly level, in the like CPU level? This example, we add the values R2 and R3 and then save the result to R1. After that, the processor jumps to the code pointed to by the label foo. It proceeds to execute the code after the label foo. Starts out by executing the instruction add R3, R1, R4. It then proceeds to execute subsequent instructions. Program counter. So the address of the next instruction is stored in the program counter register, right? From what I remember in the CPU, there's also another register called program counter which stores the next instruction. Then branch sets the instruction of that to foo, right? Sets the next instruction to going to foo. SimpleRisc has two conditional branch instructions. Branch if equal and branch if greater than. A1 instruction sets typically have more branch instructions. Nonetheless, at the cost of the code size, these two instructions are sufficient for implementing all types of branches. The branch if equal instruction stands for branch if equal. So it will only branch, like branch to full, branch if equal full will only branch if the bit over here is set to 1. Similarly, branch if greater than if this bit over here is set to 1. Write an iterative program to compute the factorial of a number stored in R0. Assume that the number is greater than 2. Save the result in R1. Okay, let's try this. Save the result in R1. The number is stored in R0. Assume that the number is greater than 2 and save the result in R1. So multiply save the result in R1. Oh, okay, I have an idea. Move R1 1. So we store 1 to R1. We store 1 to R1. We multiply what is stored in R1 with R0, which is the number. We're assuming it's greater than 2. Let me think about this. So we store in R1 1. Store in R2 2. So 1, 2. We multiply them, we store it in R1. And wait, this factorial. 1, 2, multiply, branch to factorial. Branch to factorial. Actually, no. No, this is wrong. Move R1 1. Move R2 2. So factorial 1 times 2. Store it in here. And then no, we just keep multiplying it by 2. It doesn't increase though. I have an idea. We store 2 to R1. We subtract. Okay, destination is R2. We subtract what is stored in R1 with 1. So R2 stores 1, 1 less than R1. And then what is stored in R1, we multiply it with R2. Basically, what I'm trying to do is zero, 1, 2, 2, subtract 1. So these two will multiply. This will store 2. Will store 2 minus 1, 1. No, this is an issue. This won't work. Need to go back. Store 3 instead. So 3 in R1, 2 here. 3 times 2 So we multiply 3 times 2, right? Okay, wait. How about this? R2 contains 1. R2 contains 1. How about this? How about this? You're multiplying the number that is stored in R0, right? So is stored in R2, R0 minus 1. Then we store in R1, R0 times R2. R1 stores the solution, right? Save the result too. So, and then we subtract R0 by 1. Okay, let's think about this. So, if R0 contained 5, we store in R2 1 less than that. 4. Then R1 contains 5 times 4. Okay, I have another idea. So what if we move R1 to we move the value from R0 to R1. We decrement R0. Then we multiply what is currently stored with the new value. So what's going to happen now? So what's going to happen now is that 5 is stored in R0. First, we will store what is stored in R0 to R1. Then we will decrement this 4. And then we will multiply R1 with R0. So now this will be 5 times 4. And now we will decrement this. So this will become 3. And now this will be 5 times 4 times 3. And then we will decrement this. It will be 2. And then 5 times 3 times 2 and so on. But when will this end though? So this loop, this will end when R0 is equal to 1. So we compare R0 with 1, branch if greater than. R0 is greater than 1, then it will loop. The moment R0 reaches 1, the loop will stop. Yeah, I think this works, right? Yeah, I think my solution works. If I had a SimpleRisc emulator, maybe if someone in chat can send me a SimpleRisc emulator, that would be great. And an assembly program to find out if the number stored in R1 is a prime number. Assume it is greater than 3. Save the Boolean result in R0. So save the Boolean result in R0. Move 2 to R2. So we mod it with R1, compare equal, we move to not prime. Otherwise, we add it to 1. Compare with the number. Wait. Oh yeah, it goes on till here. Greater than low. Not prime, move R00. Exit. Okay. Now that we have seen the generic instruction operand and addressing modes, let us come to one of the most advanced features in high-level programming languages that make their structure extremely modular, namely functions. Also referred to as subroutines or procedures. I mean, the correct wording is procedure because function is like they do some mathematical thing and they return one value. If the same piece of code is used at different points in a program, then it can be encapsulated in a function. Function is something like if it doesn't have side effects, right? Following example shows a function in C to add two numbers. It is now go over the basic requirements to implement a simple function. Let us assume that an instruction with an address A calls to function foo. After executing function foo, we need to come back to the instruction immediately after the instruction at A. The address of this instruction is A plus 4. If we assume that the instruction at A is 4 bytes long, this process is known as returning from a function and the address A plus 4 is known as the return address. It is the return address, the address of the instruction that a process needs to branch to if after executing a function. There are two fundamental aspects of implementing a function. The first is the process of invoking or calling a function. Second aspect deals with returning from a function. Let us consider the process of calling a function in a bit more detail. A function is essentially a block of assembly code. Calling a function is essentially making the PC point to the start of this block of code. We have already seen a method to implement this functionality when we discussed branch instructions. Okay, my internet was going down for some reason. It has gone back up again, but when it goes back down, I'll see what I can do. Uh, the label should be associated with the first instruction in a function. Calling a function is as simple as branching to the label at the beginning of a function. However, this is only a part of the story. We need to implement the return functionality as well. Hence, we cannot use an unconditional branch instruction to implement a function call. Let us thus propose a dedicated function call instruction that branches to the beginning of a function and simultaneously saves the address to that the function needs to return to. Let us consider the following C code. Assume that each C statement corresponds to one line of assembly code. So A foo and C is A plus B. In this small code snippet, we use a function call instruction to call foo. The return address is the address of the instruction in line 2. It is necessary for the call instruction to save the return address in a dedicated storage location such that it can be retrieved later. Most RISC instruction set have a dedicated register known as the return address to save the return address. So this is this, right? The last bit. But how do we know if we are done with the function? Do we just use the branch statement for that? And if foo calls another function, in this case, the value of RA will get overwritten. We will look at this issue later. Let us consider the problem of passing in arguments to a function and getting return values back. Assume that a function foo invokes a function foo bar. Foo is called the caller, foo bar is called the callee. Note that the caller-callee relationships are not fixed. It is possible for foo to call foo bar, and also possible for foo bar to call foo in the same program. Caller and callee are decided for a single function call based on which function is invoking the other. Both the caller and callee see the same view of registers. Consequently, we can pass arguments through the registers. Likewise, pass the return values through registers also. However, there are several issues in this simple idea as we enumerate below. A function can take more than 16 arguments. This is more than the number of general purpose registers. Function can return a large amount of data. A callee might overwrite registers that the caller might require in the future. We thus observe that passing arguments and returning values through registers works only for simple cases. It is not a very flexible and generic solution. Nonetheless, there are two requirements that emerge from our discussion. Space problem, we need extra space to send and return more arguments. Override problem, we need to ensure that the callee does not override the registers of the caller. I mean, we save the previous work into main memory, right? To solve both the problems, we need to take a deeper look at how functions really work. You can think of foo as a black box to begin with. It takes a list of arguments and returns a set of values. Perform its job, foo can take 1 nanosecond or 1 week or even 1 year. Foo might call other functions to do its job, send data to IO devices, and access memory locations. To summarize, a generic function processes the arguments, reads and writes values from memory and IO devices if required, and then returns the result. Regarding memory and IO devices, we are not particularly concerned at this point of time. There is a large amount of memory available, and space is not a major constraint. Reading and writing IO devices is also typically not associated with space constraints. The main issue is with registers because they are in short supply. Let us solve the space problem. We can transfer values through both registers and memory. For simplicity, if we need to transfer a small amount of data, we can use register. Otherwise, we transfer them through memory. Similarly, for return values, we can transfer values through memory. We are not limited by space constraints if we use memory to transfer data. However, this approach suffers from lack of flexibility. This is because there has to be strict agreement between the caller and callee regarding the memory locations to be used. And then we cannot use a fixed set of memory locations because it is possible for the callee to recursively call itself. An astute reader might argue it is possible for the callee to read arguments from memory and transfer them into some temporary area in memory and then call other functions. However, such approach are not elegant and not very efficient. At this point, we can conclude that we have solved the space problem partially. If we need to transfer a few values between the caller and callee or vice versa, we can use registers. However, in the argument, return values do not fit in the available registers. We need to transfer them through memory. For transferring data through memory, we need an elegant solution that does not require a strict agreement. So 3.3.10. Okay. The notion of saving registers in memory and later restoring them is known as register spilling. To solve the override problem, there are two solutions. First is that the caller can save the set of registers it requires at a dedicated location in memory. Caller can save the set of registers it requires at a dedicated a dedicated location in memory. It can later retrieve its set of registers after the callee finishes and returns control to the caller. I don't understand this diagram. Second solution is for the callee to save and store its registers that it will require. Both the approaches are shown in figure 3.9. Because if the caller saves the registers the callee requires, the caller will save the register, call the callee, and then restore the register. Or the caller can call the callee, and the callee will save the register. At the end, restore the register. Both the caller and callee need to have a strict agreement on the locations in memory that need to be used. We simplify the process of passing arguments to and from a function and saving and restoring the register using the dedicated locations in a memory. However, this solution was found to be inflexible and it can be quite complex to implement for real world programs. To simplify this idea, let's find a pattern in function calls. Typical C or Java program starts with a main function. This function then calls other functions, which might in turn call other functions. Finally, the execution terminates when the main function exits. Each function defines a set of local variables or perform a computation on these variables, the function arguments. It might also call other functions. Finally, the function returns a value and really a set of values. Note that after a function terminates, the local variable and the arguments are not required anymore. Hence, if some of these variables or arguments were saved in memory, we need to reclaim the space. Secondly, if the function has spilled registers, then these memory locations also need to be freed after it exits. Lastly, we know that if the callee calls another function, then it will need to save the value of the return address register in memory. We will need to free this location also after the function exits. It is best to save of these pieces of information contiguously in a single region of memory. This is known as the activation block of a function. The activation block is like somewhere in the stack, space is reserved for the function itself. Uh, the activation block contains the arguments, return address, and register spill area, and the local variables. Once a function terminates, it is possible to get rid of the activation block entirely. If a function wants to return some values, then it can either do so using registers. However, if it wants to return a large structure, then it can write it into the activation block of the caller. The caller can supply a location within its activation block where this data can be written. We shall see it is possible to do this more elegantly. We can have one memory region where all activation blocks are stored in contiguous region. Let us consider an example. Let us assume that function foo calls function foo bar, which in turn calls foo bar bar. The 3.11 shows the state of memory at 4 points. Oh, that's why it's called a stack. That's why it's called a stack. We observe that there is a first in, first out behavior in this memory region. The function that was invoked the last is the first function to finish. Such a last in, first out structure is traditionally known as a stack. Hence, the memory region dedicated to saving activation blocks is known as the stack. Traditionally, the stack has been considered to be downward growing. This means that the activation block of the main function starts at a very high location and new activation blocks are added just below existing activation blocks. Thus, the top of the stack is actually the smallest address in the stack, and the bottom is the largest. stack in main memory that saves all activation blocks in a program that's traditionally considered to be downward growing. We need to push its activation block to the stack. The function finishes execution. We need to pop its activation block of the stack. The stack pointer register maintains a pointer to the top of the stack. Most architectures save a pointer to the top of the stack in a dedicated register called a stack pointer. This register in R14 is in this stack pointer. This register is R14 in SimpleRisc. Okay. Note that for a lot of architectures, the stack is a software structure. For them, the hardware is not aware of the stack. However, for some architectures, such as x86, the hardware is aware of the stack and uses it to push the return address or values of the other registers. However, even in the case the hardware is not aware of the contents of each activation block, the structure is dedicated by the assembly programmer or the compiler. In all cases, the compiler needs to explicitly add assembly instructions to manage the stack. Creating new activation block for the callee involves the following steps. Decrement the stack pointer by the size of the activation block. Copy the values of the argument. Initialize any local variables by writing their corresponding memory locations if required. Spill any registers if required. It is necessary to destroy the activation block upon returning from a function. This can be trivially done by adding the size of the activation block to the stack pointer. By using a stack, we have solved all of our problems. The caller and callee cannot override each other's local variables. The local variables are stored in the activation block, which do not overlap. SimpleRisc has two instructions for functions, call and return. Call instruction takes a single argument, the label of the first instruction of the function. It transfers control to the label and saves the return address in RA. Okay, so then the function label runs, and then when it's done, saves the return value to RA. Return instruction transfers the contents of RA to PC. Okay. So calling the caller would do its thing, and then finally, so call the caller will do its thing. Call foo does its thing. I'll call it foo. Foo does some computation, and then return address PC for how does it set the return value? Control to label and save the return address and register for. Yeah, I understand that foo does its thing, and when it goes back to the caller, this foo is the callee. When it unwinds and goes back to the caller, the value returned by foo gets saved to the return address. Or maybe not. Return address PC plus 4. The return instruction transfers the contents of array to the PC. It's a zero address instruction because it does not require any operand. In table 3.9, we assume that the address method provides the address of the first instruction of the foo function. The address method provides the address of the first instruction of the foo function. Second, the return address is equal to PC plus 4 because we assume that each instruction is 4 byte long. Call and return can be thought of as branch instructions because they change the value of the PC. However, they are not dependent on any condition such as the value stored in a register. Hence, these instructions are conceptually unconditional branch instructions. Write a function in SimpleRisc that adds the value R0 and R1 and saves it to R2. Save it to R2 and then return. Return means you're going back to the, so this is the callee. Then return means we are going back to the caller. Going back to the caller means we are going to the PC is pointing to the address stored in RA, right? Then PC is the next instruction. Write a function foo in SimpleRisc that adds the values in R0 and R1, save the result in R2. Then write another function that invokes this function. The invoking function needs to first set R0 to 3, R1 to 5, then invoke foo. After foo returns, it needs to add 10 to the result of foo and finally save the sum in R3. So we return. What does this return do? We return, but the main will not execute, right? After foo returns, it needs to add 10. Wait, we start with the main, right? The invoking function needs to first set R0 to 3 because this is, we start with the main, set to 3, set to 5, and then call foo. Foo adds it and then return. We return back to main. We call foo, so the PC points to foo. So what call does is point the PC to foo and set the return address to main. We do foo, return back to main. Then we add this. So foo, the PC is set to the address of foo, okay. So call the PC is set to the address of foo. So the next instruction will be foo, and then the return, this also sets the return address to main. I don't understand this PC plus 4. The return address is equal to PC plus 4 because we assume that each instruction is 4 byte long. Each instruction is 4 byte long. Um, that PC stores the address of 4. Address of 4 plus 4 bytes is the address of main. Is that what they're saying? The NOP instruction. Let us now add an instruction called NOP that does nothing. Like other instructions, we do not need a table explaining the semantics because it does absolutely nothing. So why add this function? We will justify the need to have an NOP instruction in our portfolio of instructions chapter 10. Principle of pipelining. It is important to have an instruction that does nothing, that does not do anything to ensure correctness and execution. Let us for the time being bear with this instruction. So let us now consider the problem of loading 32-bit constants into a register. The following code snippet shows us how to load the constant. This. So we have FP12, move to R0, load the upper 2 byte, left shift. How long can the immediate value be? Like what's the size of this? And then the instruction are 30. The instruction themselves are 32 bits, right? Shift, left shift, okay. And then we move it to R1, R1, 16, left shift 16. Okay, wait. They load R1, they shifted left, and then they shifted back right. We end up with this bunch of zeros at the front. Okay. And then load all the 4 bytes. This problem requires 6 instructions that the reader needs to know that loading constants is a common operation in programs. Hence, let us devise a mechanism to speed up the process and load a constant in a register into operations. Most assemblers provide directives to directly load constants. Nevertheless, these directives need to get translated into a basic sequence of assembly instructions. Directives do not fundamentally solve our problems of loading constants into registers of memory locations efficiently. We shall achieve this by using modifiers. Let us assign a modifier u or h to an ALU instruction other than shift instructions. By default, we assume that when we load a 16-bit immediate into a 32-bit register, the process automatically performs sign extension. This means that it sets each of these 16 most significant bits to the sign of the immediate. This preserves the value of the immediate. For example, if our immediate is equal to -2, then its hexadecimal representation is FFFE. If we try to store it in register, then in effect we are storing FFFFFFE. Let us have two additional modes. Let us add the suffix u to an instruction to make it interpret the immediate as an unsigned integer. For example, instruction move u will load this into register R0. This suffix allows us to specify 16-bit unsigned immediate values. Now let us add the suffix h to an instruction to instruct it to move the 16-bit immediate value into the upper half of the register. R0 effectively loads this. Wait, what do we call U and H? Modifier U and H. U stands for unsigned. What does H stand for? Upper half. We can use modifiers with an ALU instruction, with all ALU instruction except shift instructions. Let us now consider the previous example of loading a 32-bit constant into a register. We can implement it with two instructions as follows. R0. So move H and add unsigned. By using modifiers, we can put constants in two instructions rather than six. Furthermore, it is possible to create generic routines using modifiers that can set the value of any single byte in a 4-byte register. These routines will require a lesser number of instructions due to use of modifiers. Let us now try to encode each instruction into a 32-bit value. We observe that we have instructions in 0, 1, 2, and 3 address formats. Secondly, some instructions take immediate values. Hence, we need to divide 32 bits into multiple fields. Let us try to encode the type of instruction. Since there are 21 instructions, we require 5 bits to encode the type of the instruction type. Hold on. 5 bits to encode the instruction type. Why 5? What is 2 to the power of 5 is 32. Okay, okay. Okay, so anyways, 5 bits to encode the instruction type. The code for each instruction is shown in table 3.10. I can use the 5 most significant bit in a 32-bit field to specify the instruction type. Code for an instruction is also known as its opcode. So the opcode is the unique ones and zeros, right? The 2-0 address instruction that we have are return and op. The opcode is specified by the 5 most significant bit. In this case, it is equal to 10100 for red and 10001101 for NOP. Hold on a minute. Okay, okay. Data encoding is shown in the figure 3.12. We only need to specify the 5-bit opcode in the most significant bit. The rest 27 bits are not required. So add. So opcode is using the first 5. The one address instruction that we have are call B branch if equal and branch if greater than. SimpleRisc assembly, they take a label as an argument. While encoding the instruction, we need to specify the address of the label as the argument. The address of the label is the same as the address of an instruction that it is pointing to. If the line after the label is empty, then we need to consider the next assembly statement that has an instruction. These four instructions require 5 bits for their opcode. The remaining 27 bits can be used for address. Note that a memory address is 32 bits long, hence we cannot cover the address space with 27 bits. However, we can make two key optimization. The first is that we can assume PC relative addressing. We can assume that 27 bits specify an offset with respect to the current PC. The branch statements in modern programs are generated because of for while loops or if statements. On these constructions, the branch target is typically within a range of several hundred instructions. If we have 27 bits to specify the offset, and we assume it is a 2's complement number, the maximum offset in any direction is 2 to the power of 26. So more than sufficient for almost all programs. There is another important observation to be made. An instruction takes 4 bytes. We assume that all instructions are aligned to 4 bytes boundaries. Then all starting memory addresses of instructions will be a multiple of 4. Hence, the least 2 significant binary digits of the address will be 00. There is a reason for wasting bits in trying to specify them. We can assume that the 25 bits specify the offset of the address of the memory word. Of the memory word that contains the instruction. With this optimization, the offset from the PC in terms of bytes becomes 29 bits. This number should suffice for even the largest programs. Just in case there is a pathological example in which the branch target is more than 2 to the power of 28 bytes away, then the assembler needs to change the branches such that one branch will call another branch and so on. However, this would be a very rare case. The encoding for this instruction is shown below. 5 or 27 is the offset. Coding of one address instruction. Okay, I want to see an example of this. Note that the one address instruction format finds a use for the unused bits in the zero address format. You can think of the zero address format for the return instruction as a special case of the one address format. It is referred to as one address format is the branch format. Let us name the fields in this format. Let us call the opcode portion of the format as OP and the offset as offset. The opcode field contains the bits in position 28 to 32. The offset field contains the bit in positions 1 to 27. Let us consider 3 address instructions first. Then look at other types of instruction. The 3 address instructions in SimpleRisc are add, sum, divide, mod, and or left shift, right shift, arithmetic right. It is considered a generic 3 address instruction. It has a destination, one input, and then one source, which can be a register or an immediate. We need to devote 1 bit to find out if the second source operand is a register or an immediate. Let us call this I bit and specify it just after the opcode in the instruction. I is 1, then it's an immediate. If I is 0, then the second source is a register. Let us now consider the case of 3 address registers that have their second source operand as a register I0. Since we have 16 registers, we require 4 bits to uniquely specify each register. Register Ri can be encoded as an unsigned 4-bit binary equivalent of I. Hence, to specify destination register and 2 input source registers, we require 12 bits. I don't get this part, register Ri. Since we have 16 bits, we require 4 bits to uniquely specify each register. Register I can be encoded as a 4. Yeah, now I get it. 4-bit binary equivalent of I. Okay, okay. We require 12 bits for each destination and source. The structure is shown in figure 3.14. Wait, for the previous one, for the branch one, why did it say 32 bits? Are they talking about memory in main memory? Memory address is 32 bits. And then the register is 4-bit. Branching is done with the main memory. Whenever you branch, we are using the PC, right? So if I in assembly I write branch if equal foo, what does foo get converted into? Is it just the offset? Let us consider this instruction format as the register format, like the branch format that is named the different fields OP, I, RD, uh, destination register, R source 1, R source 2. Now, if we assume that the second source operand is an immediate, then we need to set I to 1. Let us calculate the number of bits we have left for specifying the immediate. We have already devoted 5 bits for the opcode, 1 bit for I, 4 bits for destination, 4 bits for the first source register. In all, we have expanded 14 bits. Hence, out of 32 bits, we are left with 18 bits. We have proposed to divide the 18 bits into 2 parts, 2-bit and 16 bits. Wait, hold on. Out of 32 bits, we are left with 18 bits. Specify the immediate. Y for opcode, 1 for I, 1 for immediate, 4 for destination, and 4 for first source register, right? So we used 14 and we are left with 18. We can use the rest to specify the immediate. We are proposed to divide 18 bits into 2 parts, 2 bit for the modifier, and 16 bits for the constant. Okay, opcode, whether it's immediate or register, destination, source, and then second source. And if it's an immediate, we can use all this for the immediate value. 5144 is 14, and the rest 14 bit can be used for immediate. If it is an immediate, no, 5144 is 14. Wait, what? 5144. We used 14, and then there are 18 left. 18 left. And what is the modified bit? The two modified bits can take 3 values 0, 0, 1, or 1, 0. Unsigned or H. Unsigned. Okay, and then H we are. Okay. H means we are filling from this side, right? And then unsigned means we are filling from this side while this side remains 0. The remaining 16 bits are used to specify 16 bits of 2's complement number when we are using default modifiers. For U and H modifier, we assume that the 16-bit constant in the immediate field is an unsigned number. The rest of this book, we assume that the immediate field is 18 bits long with the modifier part and a constant part. Process internally expands the immediate to a 32-bit value in accordance with the modifier. Let us encode each field of the instruction. So sub R1, R2, and 3. So sub I and R1, sub the encoding is this. Immediate, yes. R1 is this, and then R2, no, sub, immediate, yes, R1, then R2 stores. This is the first source, and this is the number. The binary encoding is 0001 for the, yeah, for R1, then 0010 for R2, and then the rest is to specify 3. The compare instruction has two source operands. The second source operand can be a register or an immediate. We'll use the standard 3 address register and immediate format for encoding the compare instruction. The destination register field will remain empty. Compare instruction has two source operands. Second source operand can be a register or an immediate. Compare. We will use the standard 3 address register or immediate format for encoding the compare instruction. The destination field will remain empty. Compare, not, and move. Compare, there is no destination. We skip these 4. 4 for source and the rest 18 for immediate or R2. One of our aims in designing the encoding is to keep things as simple and regular as possible, such that the processor can decode the instruction very easily. We could have designed a separate encoding for a 2 address instruction such as compare, however, the gains would have been negligible. Not and move instructions have one destination register. Not and then can use the immediate or the source register. One destination and one source. In SimpleRisc, the instruction load and store are 2 address instructions. The second operand points to a memory address. It uses a base offset addressing mode. There is a base register and an integer offset. For a load instruction, there are 3 unique pieces of information that need to be encoded: destination register, base register, and offset. In this case, we propose to use the 3 address immediate format. The I bit is set to 1 because we need to specify an offset. The first source register represents the base register and the immediate represents the offset. Note that this encoding follows our principle of regularity and simplicity. Our aim is to reuse the 3 address register and immediate formats for as many instructions as possible. Now let us look at store instructions. Store instructions are slightly special in the sense that they do not have a destination register. The destination of a source instruction is a memory location. This information cannot be encoded in the immediate format. However, for reasons of simplicity, we want to stick to formats that we have defined. We need to take a crucial design decision here by answering question 5. Should we define a new instruction format for the store instruction? Let us adjudge this case in the favor of not introducing a new format. Let us try to reuse the immediate format. The immediate format has 4 fields: OP, destination, source, and immediate. The OP field need not to be touched. But shouldn't the OP field contain the load and store? We assume that the format of the store instruction is strd immediate rs1. In this case, the field RD represents the register to be stored. Like the load instruction, we can keep the base register as +1 and use the immediate fee to specify the offset. We break the pattern we have been following up till now by saving a source register in RD, which is meant to save a destination register. Or maybe we are compelled to do this at the cost of not introducing a new instruction format. Such trade-offs need to be made continuously. You also have to balance the twin objective of elegance and efficiency. I need to see a diagram of this. So load opcode, immediate, RD, and RS. So what is the trade-off they're talking about? Break the pattern till now by saving a source register in RD. Oh, for this code, this is going to be used to for the address in memory, and this is going to be used for what we are storing. So we are storing the value stored. We are storing the value saved in register RD to this memory location. So this is an exception in that it is being used as a source, and all this is being used as a destination. Okay, I understand. The last few subsections, we have described a method to encode an instruction into a sequence of bits. A compiler can use this method to translate a program written in a higher level language to machine code, thus create an executable format. It is now the job of the processor to execute this program by reading the instructions one by one. We have made our life substantially easy by assuming that each instruction is exactly 4 bytes long. The processor needs to start at the starting address of the program in memory and fetch one instruction after the other. If an instruction is a branch, then the processor needs to evaluate the branch condition and jump to the branch target. Part of the processor that is primarily concerned about the details of the ISA is to decode logic or the decoder. It is the role of the decoder to understand and decode an instruction. While designing and encoding for an RSA, creating a simple, efficient instruction decoder was our prime objective. To decode a simple RSA instruction, the first task is to find the instruction format. We have defined 3 formats: branch, immediate, register. The 6 branch format instruction are called return, branch equal, branch greater than, B, and NOP. The opcodes of all 5 branch instructions have 1 as their most significant bit. Branch, offset, register, then immediate. These are the 3 formats. Hence, for a decoder to find out if an instruction is a branch is very easy. It just needs to take a look at the 3 most significant bit of the opcode. An instruction is not branch, then it must be an immediate or register. Or we can use the I bit for that. We can use this bit for that, checking immediate or not. Now that we have designed a small instruction set of our own, looked at sample programs and encoded our instructions, we are all set to design a processor for our SimpleRisc ISA. It needs to decode every single instruction and execute it accordingly. Before proceeding further, let us look back at how we designed our ISA. And how should ISAs be designed in general? The first step in designing an ISA is to study the workload that the ISA is being designed for. In the case of SimpleRisc, we wanted to use it for running general purpose programs. This meant that SimpleRisc needed to be simple, concise, generic, and complete. After studying the workload, we need to next decide on the number of instructions that we need to have. Unless there's a compelling requirement Otherwise, it is not advisable to have more than 64 to 128 instructions. More than 128 instructions will make the instruction decoder very complex. After finalizing the number of instructions, we need to finalize the different types of instructions. If we are designing an ISA for extensive numerical computation, then we should have many arithmetic operations. If we are designing an ISA for processing text, then we should have many instructions that can process strings. In the case of SimpleRisc, we devoted 6 instructions to arithmetic, 3 to shift, 3 to logical operations, 3 data transfer, and 5 branch, and 1 designated as no. We chose this distribution because we expect to run a lot of general purpose programs that will have this complex arithmetic and logical constructs. Once we have finalized the broad type of instruction distribution of instructions across these types, we come to the action instructions themselves. In this case, we want to make the common case fast. For example, there's no point in having a division instruction in programs that do not have division operations. Second, we need to decide the format of each instructions in terms of the number and types of operand. For example, in SimpleRisc, all our arithmetic operations are in the 3 address format. There is a requirement from the side of the processor designer that they want to reduce the number of registers, then we can opt for 2 address format. Once the format of the instruction is decided, then we need to decide on different addressing modes. This decision has many ramifications. For example, if we allow register indirect addressing mode in arithmetic instruction, then we need to add addition hardware to access the memory and fetch the operand values. On the other hand, if we have a register only addressing mode for arithmetic instructions, then their implementation will be fast. Once we have designed the set of instructions, we need to decide a proper encoding for it. The main aim should be to reduce the work of the instruction decoder. Alrighty then. I think that's it then. I mean, if these exercises had answers, I would have probably done them because I want to check the answers as well. That's for this chapter. Next time, I will start studying about the ARM assembly language. And yeah, I'll end this stream here then. I will see you guys next time. Bye.